Hi and welcome, ladies and gentlemen. Today we are talking about breadth first search in graphs. Well, let's start right into it with an example. Well, our graph is, as you see here, A, B, C, D, E, and F with some edges between them, and we want to search for the value F in our graph. And for that we need to give our algorithm a start node we want to start at for iterating all the children of our graph. In this case, I want to use A as a start node and F as a search node. So when we want to do breadth first search, then we start with the current vertex as A, that is our start node. And then we want to create a list of children of our start node, and that is here B, C, and D. And then we have a look, is A our value, our search value? If it is not, then we can return and say A isn't it, and we can keep going with the next node in our queue. So in this case, that is node B. B has no children, so we simply remove B from our queue. And then have a look, is B our search value? No, it is not. So we keep going with the next node in our queue. That is C here, and there we have the problem that C has the child D, but D is also already in our queue we are working on. So that's why we also keep a list of already worked on nodes, so we don't have to work on any node twice. So in this case, we don't append the new D, we just work on C. C is not our search value, so we keep going in our queue. And so we work now on D, and then we append all the children of D to our queue, in this case E and F. From that point we check, is D our search value? No, it is not, so we need to go to the next element in the queue, that was E, and then E has no children, so the queue stays F. So E is not our search value, so we need to keep going with the next node in our queue. In this case, it is F. So our queue is now empty because F has no children, and we find our search value here. If our search value wouldn't have been in the graph, then we would have stopped here, because we simply didn't find the value in our graph. Alright, the algorithm would look like this, that we check for the current node if it is the search value, and if it doesn't, then we append all the children to our queue, and then we go through the first child, which is always the first element in our queue, and then to the next, and so on. So let's implement that in Python. For that, I create a new Python file called breadth first search.python, and as usual you find the source code in my GitHub repository. The link is down in the description below. Well, for the breadth first search algorithm, I want to use the source code of another video. I blended it now, that is the adjacent graph video that I made, and I want to use the basic graph algorithm that I used there. So for that, I copy that here. It works like this, that we have our graph class, and in that we have a vertex class that stores an index and a name, and we have an edge class that stores the vertices, and a vertex always has a node from, a node to, and a weight attribute. And with that we can create our adjacent matrix in the end. Alright, so from here on I also want the print adjacent matrix function here. I just need to copy that quick, and we need the main class. That is this one here. And in the main class we will have the same graph as in our example. So now I go in and say def breadth first search BFS, and this gets the self value, it gets the start node, and it gets, here better say start node name, because it will be the actual value of the node, not the index or the node itself. And so we also need a search value. And we say here performs a breadth first search on the graph. And we can say returns true if the search value was found, otherwise false. So, alright, from there at first we need to convert our start node name and our search value into, or just our start node name into indices. And there I say start index is equal to, and there I go x.index 4, and there I say x in self.nodes. Self.nodes is a class property which stores all our nodes. So, and also we have to say if here start node name is equal to x.name. Or was it x.name or was it x.value? It was x.name, so that is completely fine. Alright, so what else do we need? We need our queue, and our queue will initially just have our start index in it. And we also want a list of visited nodes, so we say here visited or vertices. And that is from the beginning empty. Alright, so good so far. Now we can actually have a look at our children in the graph and our actual search value and how we perform that. So first we say while the queue is not empty, so I want to see here, or say here, that while the length is greater than 0, which is the same as saying our queue is not empty. Then I say queue, before we need to do, we need to go in and say current node equals queue 0, which is always the first element in our queue what we are working on. And then I can straight away remove this element from our queue, so I say our queue is our queue from the first element on. And after that I want to go in and say visited vertices dot append our current node. So now we prepared everything as we needed. Now we can check if. And there we need to use also a different mapping now, and that is from our index we are working on to our actual value or our name of the node. So I say here index name mapping is equal, and there I want to use a dictionary x.index, and I want x.name 4, and there I want to have x in nodes, and that creates a dictionary which has as a key value the index of a node, and as a value it has the name. Alright, and there I can say if index name mapping of our current node, which is the index actually of the current node, is equal to, and then I want to say search value. Then I say return true because we found our value. Else, now we can say here value found, or we can go in here and say proceed with the children. And here I actually have to have a look at the adjacent matrix because we are working with our indices. So I want to go in here and say our adjacent matrix is equal to self.getAdjacent matrix, and that will give us the adjacent matrix of our graph in the end. And there is one little speciality in this adjacent matrix. If the edge value is 0, then we say there is no edge from from one node to the other in our adjacent matrix. So I say here, if adjacent matrix of current node and our children, so I go in here and say for I in range, and there I can use the length of our adjacent matrix. An adjacent matrix is always a quadratic matrix, so the adjacent matrix, it doesn't matter if we take the amount of rows or the amount of columns. And here I say it's the ith child, so, and I want to check if that is unequal to 0. Then I want to go through our, then I want to add it to our queue. Then I say queue dot append I, and then we can work on this index. And I also want to add something else here, and that is the visited vertices list, that we check that we didn't work on this actual child already. So I can say here and then I want to go in the next line, visited vertices, so I in visited vertices, and we actually want that not. So we say our child is not in the visited vertices. Then we add it to our queue. So that's basically it. Then we just can return here when we are done with our while loop false, because we never give back true as here, so we didn't find our value. So here we have g.breadth_first_search BFS, and there we give it our start node and our search value. So let's run it and see if it works. And we still have a little error here in line 98. And here is our mistake, because we have here a list as a start index and we want there 0 as an index. And that is just because we figure out our start index here, and that is creates a list with just this one index in it, but we have there to take the first element. So if we run it now, then it should work. And here we get a false because we are looking for G in our graph, but that has just the nodes from A to F. And if I go in and search for F, then it should work completely fine and we get true back. Well, ladies and gentlemen, that's it for this video. If you liked it, give it a thumbs up and subscribe to the channel whenever you want to get informed about new videos that I upload. So that's it for me today. Have a great day. Bye.